It's hard to say exactly what the signal was, but clearly there was something that suggested deception. And even though it would be difficult to define it precisely, I think we can all agree that there's no doubt there was some sort of a signal. Now, a common misconception is that this sort of signaling occurs primarily with the face. Consider this image. How many of you think he's feeling positive? Good. How many of you think he's feeling bad? Once we see the whole image, it becomes much clearer. How about now? Good or bad? The facial expressions in both of these examples are very similar, but we needed the body to disambiguate his emotional state. This is an extreme example, but the body provides strong context to disambiguate the subtle differences in our social signaling all the time. All right, final example. In this interaction, the child thinks he's playing with the examiner, but she's actually testing to see if he's at risk of autism. She gives him the ball, and he sends it back, but she holds it until he requests for it in some way, and you'll see he'll nod his head momentarily. There. She accepts this as a gesture of request, and then she holds it again, and he does something really interesting with his hands. Just watch his hands. He does this subtle gesture, just opens his hands slightly like this, and she accepts this as a request. It's really fascinating to me that across cultures, age groups, ethnicities, gender, we all immediately understand what this gesture means. The 2-year-old child knew to do it, and even knew that the examiner would understand what the gesture means. And yet there's no unique word for this gesture in any language. And there's nothing unique about this gesture. There are likely hundreds of thousands of such unnamed behaviors that we continuously exchange and effortlessly interpret without even realizing it. This is what the eminent anthropologist Edward Sapir described as an elaborate code that's written nowhere, known to no one, and understood by all. When we interact with one another, we are continually, effortlessly, and subconsciously transmitting and receiving all the subtle elements of the elaborate code. It's what makes a social interaction feel real and immediate. And to produce interactions in VR that feel just as real and immediate, we need a computational understanding of Sapir's elaborate code. And this is really complex, because we need to discover the vocabulary, the syntax, the morphology, the synchrony of social behavior, and all the other structures that we don't even know about. So where are we today in being able to capture the elaborate code? As we saw during Shep's demo, VR systems today can capture 2 major signals: the head motion and hand motion of the user. By tracking the motion of the headset, we can get some idea of what the user is paying attention to. And the touch controllers can catch hand signals like pointing and giving the thumbs up, as you see here. That's enough to do a lot of cool things, but it's only a tiny subset of all the rich and complex signals that humans send each other when they're interacting. The grand challenge in achieving full social presence in VR is how to capture and crack the rest of the elaborate code. It's key to unlocking the full potential of VR to transform our lives. Now, as I mentioned earlier, there are 3 great challenges to achieving social presence today that are nowhere near solved. To understand how they fit together, let's look at the simplest implementation of the social VR pipeline. Take 2 VR users separated by distance and connected over the network. The first challenge is capture. VR systems are usually thought of as the ultimate display, the final display. But to make social presence a reality, we have to make it the ultimate motion capture system as well. It has to be able to capture all of the subtle details of the reaction of the woman in the green jacket, the tennis player's body, the child's hands, and all the elements of the elaborate code. What makes this challenge confounding is that we can't do this with a room full of expensive devices, or ask people to wear a full motion capture suit. VR has to be affordable and convenient. And even with expensive equipment, there's no algorithm in existence today that can capture all the nuance and subtle details of the user's face, body, and hands, and do it in real time. This is an example of a capture of the mouth from cameras mounted on the VR headset looking at the mouth of the user. The video on the left drives the avatar on the right, and as you'll see, the capture algorithm works reasonably well for general expressions, but there's a lot of work to do before we can get the subtleties right, especially for speech. We need new algorithms to capture the eye motion, the hand motion, and the full body motion. And once captured, these social signals need to be transmitted and then displayed on the other side. So we can animate and render avatars that are rich and engaging as well. So display is the next challenge. The bar for photorealism in VR is incredibly high, far beyond what we've seen in any prior medium. In this example, you can see from my avatar that the general structure of the face can be captured reasonably well. But there are several important elements missing. The eyes and the mouth are notoriously difficult to get right. And of course, hair. Now I'm lucky, I'm bald, but I still had to shave for the scan. As you can see from the shaving cuts on my avatar. But there's something else that's missing in this avatar as well. And that's the real challenge. The real challenge is in getting motion right, the facial expressions of the person. There's no animation rig in the world that can capture all the nuances of facial expressions in speech, and this carries over to the body and hands as well. As this face animates, observe all the fine motion and subtle details. Notice how much you understand about his expression from those details. We need new animation and rendering algorithms that are able to reconstruct the subtleties of the elaborate code to users on the other side. The final challenge is social prediction. As the interaction progresses, every step of the VR social pipeline from capture to transmission to display will add latency. Thanks to video conferencing, we're all familiar with how disruptive these latencies can be. When a teleconference system lags, the sense of immediacy that real interactions have just disappears. To overcome latency, we need to develop new approaches to predict social behavior out, slightly into the future, so avatars will feel as natural and responsive as real people. This is particularly important for interactions over the internet, which creates latencies that can be long and highly variable. Now, if this concept of social prediction sounds impossible, consider the fact that our brains do it all the time. It's what allows us to function in the real world by continually anticipating the state of mind and intent of others. In the 1960s and 70s, researchers demonstrated this through the famous point light display experiments. If I were to ask you to guess what this collection of points is, I'd likely get as many answers as there are people in the room. Is it a face? Is it a dog? It would effectively be a Rorschach test. But interestingly, the moment the points move, the ambiguity disappears. There's now a consensus in this room about what this collection of points means. But there's more. Not only are we able to infer what was happening, we can also predict what would happen next. I'd expect we have a consensus that the next motion will be the up and down motion of a handshake, right? And astonishingly, we know this all from just the momentary motion of 20 two-dimensional points on the screen. Our brains are remarkable inference engines able to draw upon millennia of evolution and a lifetime of experience to transform these sparse points into fleshed out people in our imagination, and to predict the next actions of those imagined people as well. The challenge of making the pipeline of social VR work is to learn how to computationally do the same sort of inference and prediction. Now, these kind of pipeline diagrams produce an illusion of separation between the parts of the pipeline. But in fact, the three challenges are tightly coupled to the elaborate code that we have to discover. We need to know what is absolutely necessary to sense to build affordable, unobtrusive hardware that can capture the signals of the elaborate code. We need to know what to animate and render to convey the signal in a natural and deeply convincing way. And we need a computational understanding of the code for social prediction to overcome latency. It's a maxim of science that we first need to be able to measure what we want to predict. Cracking the code will require understanding social behavior in a far deeper way than has ever been attempted before. To do exactly that, my students and I built a facility at Carnegie Mellon University called the Panoptic Studio. It was designed to measure social interactions at the highest level of detail with over 500 precisely synchronized cameras capturing the inside of the dome.